Hello folks, today we're going to be talking about 3D geometry, and this is the subject of Chapter 7 of the Robotic Systems book. So in robotics we use 3D geometry all the time for a number of different tasks, for designing robots in CAD software, for doing physics simulation, for doing collision detection to avoid colliding with obstacles or yourself, map building, object recognition, etc. And so we need to be able to manipulate and represent these models in some sort of computationally efficient way. There's lots of different types of representations that people use in robotics, and we'll typically use geometric primitives. There's also point clouds, which come from raw data, and we're also going to be talking a lot about triangle meshes. But there are all sorts of different types of other representations that you might, if you're going to be working in robotics, you might be able to see. So for example, depth images are going to look like images like this picture in the middle here. There's also going to be convex polytopes, subdivision surfaces that represent the surface of objects, and also volumetric types of data like voxels. So for example, if you've ever played Minecraft, you'll see something like the picture down on the bottom, but there's also other types of volumetric representations used in, for example, MRI imaging or other kinds of three-dimensional imaging. But in any case, we'll focus mostly on the three types of representations that I highlighted here in red. So in any case, when you're trying to choose some sort of geometric representation for the types of objects that you care about, you want to think about how accurately do you want to represent your geometry? What types of operations do you need to perform? Are you going to be visualizing this a lot? Are you trying to be doing, let's say, object recognition? Are you going to be doing collision detection? And how quickly and how accurately do you need these computations to be performed? If you're also working with networks especially, then you have to worry about storage and transmission limitations, although in some cases, even on a single CPU, dealing with volumetric real-time imaging, for example, can be a sort of systems problem in terms of how much bandwidth you can accommodate. And then finally, how easily and reliably, accurately and quickly can you convert some sort of source data, whether it's from your raw sensor data or CAD models, into the format that you wish to desire. And so if you're going to be doing a lot of conversions, you typically are going to have worse performance. So, if we can try to work directly with the data that we have, it's probably going to be much more efficient. So this is why point clouds are a very popular representation in robotics. So let's first start with some basic notation that's independent of the representation somewhat. So a geometry consists of some sort of volume in space. So D here is either two or three-dimensional space, and the volume here, the geometry, is some subset of that space. The surface of the geometry is just its boundary. So this is partial G represented with this symbol here. At any point on the surface, we have what's known as a tangent vector. So this, well, there's many different tangent vectors. So these are any kind of vectors that are move parallel to the surface. So in other words, this is the derivative of some curve through P on the surface of the geometry. And then finally, we have the normal. The normal is a direction that's perpendicular to all tangents of the geometry. Now, we usually speak of the outward normal. There's an inner normal that points into the object, and then the outward normal that points out. Usually we speak of the outward one. And for smooth surfaces, this is unique. Now, if the surface is not smooth, for example, if it meets at an edge or vertex, the outward normal is not well defined, but we can define other, for example, the directions that point out of the surface. Some other notation and terminology. So a convex shape is one in which if you take 2 points inside the shape, then the entire line segment in between is also within the shape. So here, these first two items, a sphere or polygon that has no kind of convex indentations, those are convex shapes. This kind of concavity inside this third shape here makes it non-convex, because if you take 2 points in that shape, then the line between them exits the shape. Collision, also known as overlap, is when you have two geometries and there is some point in the common intersection between those two. So there is some point X that belongs to both A and B. There's also the term contact, which is sometimes confused with collision. So contact occurs when there is a point of intersection, but that only lies on the surface of the two objects. Okay, so the illustration here on the right shows contact which is also collision, but the collision on the left here is not contact because the two objects overlap with some volume. The distance between two objects is the minimum distance between any 2 points picked between those two objects. Just a technical point, this is an infimum in case you have a non-closed shape, but in any case it's basically the minimum of the distances between all points in object A and also all points in object B. There's also the notion of ray casting. So if you have a certain ray, ST, passing from the source point S in the direction T minus S, then this tries to produce the first point U, the first kind of interpolation point. This could be going from 0 to infinity of the point x plus s. X is equal to s plus u times t minus s, and this has to be the first point that this ray hits the geometry. If the ray does not hit the geometry, then by convention you could call this this parameter infinity. Okay. So with that, we can start talking about different types of ways of modeling worlds. So when we have a world that is, for example, a set of objects, obstacles, a robot, maybe multiple robots, we typically represent these as collections of rigid bodies. These rigid bodies contain reference geometries, which we'll call GL, as well as their transforms T. Now, we're not going to actually transform the geometry information, but we're going to use what's known as an implicit transform representation. So the geometry itself does not change. The kind of representation that we use, for example, triangle meshes, point clouds, etc., but the transform T will change. So as the robot moves around, its transforms will change, but the underlying geometry will not. So we'll store all these objects in their kind of underlying reference frames shown here, and then they're assembled into the actual shape of the objects and the arrangement of the objects that we actually see in the world. Now, what we want to do, the reason why we do this is because there's a lot of persistent information in that local geometry. It doesn't change very much. And so we can do a lot to do calculations in the local geometry rather than in the global frame. So there's, for example, if we're trying to render this on a GPU, that information about where these vertices are and the triangles are, it's going to be done in the local frame. And then the transforms to actually draw it, render it onto the screen, those will be done on the fly with a GPU. So, but that data is actually stored in the local frame. We'll be doing the same thing with collision acceleration data structures, bounds, etc. So first, let's talk about how we do this with geometric primitives. There's many different types of primitives in use. For example, points, spheres, rays, lines, segments, triangles, boxes, cylinders, etc. But the key component of geometric primitives is that the collision and distance operations are typically quite fast, order 1 in fact. So as an example of how we might do this, we can try to calculate whether a segment and a sphere collide or what their distance is. So let's say that the sphere is represented by its center and its radius, and the segment is represented by its endpoints. The way that we figure out the distance between the segment and the sphere is that we first look at the distance between the segment and the center point C. This can be done by doing a projection operation, so we can figure out the distance along the ray AB, where the ray AC projects to orthogonally. And this is going to be denoted dA parallel, and it's given by this operation here. Now, if we subtract off this amount of movement along that ray AB from the ray AC, then we get the C perpendicular ray, shown here. Now, the C perpendicular ray is the distance from the center to the line supporting this line segment AB. And so the distance between C and the line segment is either that distance, that length of C perpendicular exactly, if that dA parallel is within the range 0 to the length of B minus A, and otherwise it's the distance between C and the line segment is the distance to the closest endpoint. And from that we can compare the distance to the radius and determine whether or not we have a collision. So for other types of geometric primitives, the types of calculations that you need to perform are quite mathematical and geometric in nature, but in any case you can do this in all in order 1 time. A similar type of geometric representation that's quite mathematical is a convex polytope. These are defined by what are known as half-plane equations. So these take some direction AI, which is an outward-facing normal of a facet of the polytope, and AI transpose x is less than or equal to some offset bi. And the set of points x that meets these equations is going to be bounding some volume in space. So it's very easy to test whether a point is inside or outside of this polytope just by evaluating these half-plane equations. It's also very easy to determine the penetration depth of a point. Distance between polytopes is fairly easy to compute, and we'll talk about how you might do that using a walking method. However, the problem is that not all objects are convex. Most objects, in fact, are not. And there are things called convex decompositions that you can use to try to represent non-convex objects using unions of convex objects. But not all objects are that easy to represent with a bunch of convex polytopes. Point clouds are another very popular representation because they are very tied to our types of 3D sensors that we use in robotics. So a point cloud is just a collection of three-dimensional points. These points P1 through Pn may also contain color information as well as other information. And the nice thing is that these can come directly from scanners, from LiDAR, stereo reconstruction, or RGBD cameras. Polygon meshes are also quite often used, and most often we use triangle meshes. So we think about an unordered list of triangles. So this is just a collection of triangles. We oftentimes store these as separate lists of vertices as well as triangle indices into the vertex list. This reduces the amount of duplication of vertices because, oftentimes if you have one triangle, you're going to have a triangle right next to it sharing two of the same vertices. This is a very ubiquitous representation used in CAD, video games, scientific visualizations, and is also what GPUs were built to process. And so for video games, we typically render millions of triangles per frame, and it can be extremely fast. So the nice thing about polygon meshes is that we're actually representing the surface. We actually have some closedness to the to the surface, whereas point clouds don't tell you anything about where the surface actually lies. They're just sample points along the surface. So regardless whether you choose point clouds or triangle meshes, you will still have issues about resolution and how accurately you can represent a given underlying geometry. So if you were to think about a resolution parameter that can govern the kind of fineness of your point cloud or fineness of your triangle mesh, the finer you make the mesh or the finer you make the point cloud, the closer you'll get to the actual geometry, but also the computational cost and storage costs will also increase. This increases by the size of the object squared for a given resolution for point clouds and polygon meshes, whereas for voxel representation, it increases with the cube of the width of the object divided by the resolution. So in order to get more efficient computations, you'll typically do some sort of downsampling for point clouds or mesh simplification for meshes, making the representation, sacrificing accuracy in the representation, but gaining computational efficiency. Another thing that we need to worry about is how do we deal with large scenes of objects. And so if we want to do operations like collision detection or simulation, we need to think about how to do collision detection between lots of different objects. So if we think about n different objects, there's order n squared possible pairs of interactions between those objects. And so in order to check collisions quickly, we need to do this more efficiently than just a brute force check. So in particular, we'll talk about spatial grids, closest feature tracking, and bounding volume hierarchy techniques. So the spatial grid is good for many small, simple objects that are about the same size. So for example, if I have pedestrians walking around and I want to figure out which ones are close to one another, I can divide up the space in X, Y into bins of size D, which are in this case boxes, or I can also look at three-dimensional grids with cubes, and I can add all the different objects into the grid and index them into which grid cell they lie in, and also each grid cell will figure out what will contain a certain set of objects inside of it. Now, if I want to ever figure out which objects are close to one another, so let's say that I look at this object here, I can look at the bins surrounding its bin, And as long as my query radius is within the width of one of these bins, all of the objects within a distance d from this one will be within one of these 9 squares here. And so I can just examine, I can reduce my my query to examine the objects that are within these bins here. So in this case, the running time becomes proportional to the number of objects, as long as the objects are well separated and not all in one bin. And also, if we're trying to do distance computations, we can also leverage this type of data structure. This is also used quite often in point cloud calculations. So for example, doing outlier rejection and normal estimation, I oftentimes use these spatial grids to figure out which points are near one another. So for example, outlier rejection would say if there's no point with no other point within some radius of my point, it's probably an outlier, just some spurious noise, and I can go ahead and toss that out. Also, if I want to do things like normal estimation, I can take, let's say this point over here, I'll put a circle around it, and I can fit some sort of plane to the points within that radius. Now the perpendicular direction to that plane can then be my normal. And so if I repeat this for all of my points, then I can then calculate my normals in order n time. So the next type of technique we'll talk about is closest feature tracking. So especially for convex objects, this is a very efficient and also optimal method for doing distance computations. So the nice thing about two convex polytopes is that the closest pair of features between the two objects doesn't move very much as they rotate. And so if I were to track the closest feature as these rotate and translate, I will only need to hop amongst fairly few steps along the surface of one of these objects. And so when the closest feature pair changes, it's going to be on the boundary of the previous closest features, and I can start marching along the boundaries to try to keep track of closest features. As an example, if I start out with 2 points that are closest, 2 vertices that are closest between the two objects, then the only changes that can be made in terms of moving from vertex-vertex closest points to something else, I could either move from a vertex to an edge to be the closest next pair, and so I only need to look at the edges emanating from this from one of the vertices to try to figure out whether this next feature point is going to change to one of the edges of this convex object. So this can be done. This change can happen from object A, but it could also be done on object B. So I have to do a kind of symmetric test here, checking to see if this vertex passes one of the planes, one of these perpendicular planes to one of these edges on object A, and I also have to do the same thing for object B. In any case, it's very fast, and oftentimes, on average, it's approximately an order 1 computation for tracking under small movements. And so this has been leveraged for self-collision detection. So especially for objects with many, many degrees of freedom, we have to do a lot of different collision pairs. We have to test lots of different collision pairs. And so having this update be really fast as the robot's undergoing certain motions means that we can calculate self-collisions very quickly. Now, lastly, we'll talk about bounding volume hierarchy methods. And the idea here is that we'll take the underlying geometry, in this case a cat, and we'll start to represent parts of the geometry using progressively larger and larger bounding volumes, in this case, a bunch of spheres. It doesn't have to be spheres, and in fact, there's lots of different types of bounding volumes that are out there, but for now, we're going to be talking about spheres just to get a sense of how this type of thing works. So the idea is this: we'll enclose the objects into bounding volumes. We'll then check, rather than checking collisions with the underlying triangles, we're going to test the bounding volumes first. If the bounding volumes don't overlap, then we can go ahead and throw out any possible collision, because the bounding volumes contain everything that's part of the geometry within it. So when we do check the bounding volumes and they do overlap, we'll then decompose the object into 2, and then we'll look at the sub-bounding volumes of the different parts of one of those objects. And we'll progressively subdivide until the objects are either known to be in collision or known not to be in collision by proving that the bounding volumes don't overlap. Okay, so how does this work exactly? So we're going to actually pre-compute these bounding volume hierarchies for each of our objects. And so we can take, for example, small bits of this, this geometry here and then build from the bottom up, or we could also do top-down construction of larger and larger bounding volumes in this case, until we eventually contain the entire object within a bounding volume. So now we have this tree. So when we have two objects that are represented by their trees, we can then try to calculate their whether they intersect or not. So in this case here, note that these don't have to be actually balanced. They don't also have to be of the same depth. In this case, the green object here doesn't have a subdivision under bounding volume C. So what we can do for collision detection is build a search tree and proceed recursively by checking these bounding volumes. So first, let's check bounding volume A versus bounding volume A. If we find that these are not in collision, we can go ahead and throw it out and say there is no collision. So within one single step, we can prune and say that there is no collision. Now, so one note to be aware of is that we're not going to actually transform the entire trees because that would be expensive. And so instead what we'll do is, because we're just expressing these bounding volume hierarchies in local coordinates, we're only going to transform the bounding volumes with the implicit transforms of the objects when needed. And so for each of these tests, we'll do that transform. Hopefully we won't have to do this transform for all of the bounding volumes and all of the underlying geometries inside the volumes. So let's say that we're in this separate situation here where A and A are now overlapping. So what we'll do is then we'll break open the, let's say, the larger one of the two. And now we have these children B and C. We can then see that, well, if we're going to check B versus A, there's going to be no collision, and so this branch can be pruned here, whereas we still have to check the subtree of C and the subtree of A. All right. So now we can, for example, break the green A into its subcomponents here, and we can then prune CB from consideration. And so then we can finally break C open, and we're now down at leaves of the tree, and we can start to, if we can find that these two leaves bounding volumes actually intersect, we can start to check the underlying geometry within those bounding volumes. Right, we're checking the content for collision. There's a couple of search strategies to make this fast. So first of all, if there is no collision, it really doesn't matter in which way we test these different bounding volumes. But if there is no collision, we must check all possible paths eventually by either pruning or finding leaf nodes and checking their contents. If there is a collision, we want to find it as quickly as possible. So it's really important for us to order our search so that we find these collisions when we can. And so one very effective greedy search strategy is to minimize, for example, this term d over rx plus ry. What this means is that we take the center of these two bounding volumes and then we take the distance. If d is small, then it means that these two centers are pretty close to one another. And if this value is large, then it means these centers are fairly far from one another. So in other words, we're trying to expand the node with largest relative overlap. So in other words, because these are containing some parts of the geometry, if these bounding volumes overlap a lot, it's likely that there's going to be collision there. Okay, so in summary, we've gone through a variety of different geometry representations. We'll most often talk about triangle meshes and point clouds in this course because they're quite versatile and also they map very closely with sensor data. We talked about the implicit transformation representation of worlds and also several different types of collision acceleration data structures. Note that all of these rely on pre-computation to make the online queries fast. I'll see you all next time.